Hello, and thank you for taking the time out to view this presentation on superstatic SG graphs. In this presentation, I will go over how you can create OGIS output objects, and then I will show you how you can use the OGIS output objects to create Kaplan-Meier plots using the template and the SG render procedures. Knowing how to create OGIS output objects will also help you not only to create Kaplan-Meier plots, but also to create other plots, such as the forest plots. I will also refer to the combination of template and SG render procedure as GTL. In this section of the presentation, you will see how to use the OGIS objects from statistical procedures to help you obtain the necessary data in order to create plots, such as the Kaplan-Meier plot. In order to obtain the data needed for your plots, it's crucial to know the output objects that you want to use. One way to get the names of the output objects is to use the OGIS trace on statement right before running the proc for your statistical procedure. The OGIS trace on statement writes to the stats log a record of each output object that is created from the subsequent procedure until OGIS trace off is used, which then suppresses the writing of the output object to the stats log. Some of the output objects created by the proc lifetest code used in this presentation are quartiles, product limit estimates, and survival plot. This slide shows an extract of what is seen in the log when using OGIS trace on right before the proc lifetest procedure. You can see that the output object survival plot is created within the lifetest procedure. For us to create a dataset of the survival output, we simply need to use OGIS output survival plot equals the name of our choice. For example, survival plot. You will see an example of using OGIS output survival plot in the upcoming slides. You can also use the help guide to find the names of all the output objects available within the procedure. Here, I've selected the lifetest procedure details tab and then selected the OGIS tables name link to see all the available table names within the lifetest procedure. Similar to the method used for OGIS table names, you can select the OGIS graph names link in the details tab to find all the OGIS graph object names. These are the OGIS graph names available to the lifetest procedure. And you can see that we use survival plot here, and that's what we're going to use in our example. Now we will see an example of how to create the OGIS output objects using the lifetest procedure. But firstly, I will show you an example of how a time to event dataset looks. So here we have ADTTEF, and this is an example of a time to event dataset. You can see we have the use subject ID variable, which denotes the subject identifiers. We have the treatment variable, which indicates which treatment the subject is in. We have a value, which is the time to event, and we have the CNSR variable, which denotes if the time to event was censored or not. And with OGIS output objects, you can create various data sets. The first data set that we are producing comes from the survival plot object. The second data set that we produced comes from the Holmes test objects, but we only want to subset specific records. We only want to show specific records, and so we are subsetting on the log rank p-value test. Now, this procedure can also produce a survival plot automatically. However, the survival plot may not meet our needs. And from my experience, 9 out of 10 times, I cannot just use the default survival plot, which is produced. I usually have to make modifications in GTL. For example, in this example, I'm not sure if you can see it, but the axis tick values goes from 0 to 200 by 50. However, I would want to produce it 0 to 210 by 30 so that it shows the survival value at every month. This statement, time AVA by sensor, is used to indicate the survival time and to indicate if any time points were censored. In this example, a value of 1 within the CNSR variable indicates that the time point is censored. We use the strata TRTPN statement because we want to produce a KM curve for each of the treatments, and there are 3 treatments in the study, so we want to do a KM curve for each of the 3 treatments. Now we'll go deeper into creating the KM curve with GTL. On this slide, there is a KM plot, and you can see the KM curves for each of the 3 treatment groups. The blue curve denotes the placebo group, the low dose group has a red curve, and the high dose group has a green curve. This plot also displays the censored legend in the right-hand corner of the graph, the top right-hand corner of the graph, and there is a box which shows the log-rank p-value and the hazard ratios between the placebo and the treatment groups. The bottom of the plot displays the patients at risk numbers. You can see that at the start of the trial, there were 86 patients in the placebo group and 84 patients in the low dose and the high dose groups. You may be wondering, how do we create a plot like this? But don't worry, I will show you. There are a few steps that we can take to produce a KM plot. The first step is to have a time to event dataset, for example, ADTTE. The second step is once you have had your time to event dataset, you can use the live test procedure to obtain the Kaplan-Meier survival dataset and also get the median survival times. If hazard ratios are also requested, you can use the PHREG procedure to obtain the hazard ratios. After you have created your hazard ratios and median survival time datasets, you can use the into clause from the SQL procedure, or you can use the call simple routine to create macro variables which have the hazard ratios and median survival times as the macro variable values. You know you can use any method you are most comfortable with to create those macro variables. The main thing is that you have these values stored as macro variables for use later when creating the graph. After you have created your macro variables, which represent the hazard ratios and the median survival times, and you have your survival data set of the survival probabilities against time, you can then use GTL to produce a plot like the one you saw in the previous slide. Now we are going to go back to the more complex example. As I'm sure you're already aware, it's usually easier to break things down into smaller steps when you want to learn them. Isn't that correct? In our example, the first step in creating a Kaplan-Meier plot is to create the KM curves, censored label, and the subjects at risk table. In this example, there are actually 2 overlay layouts. The first overlay layout produces the KM curves, and the second overlay layout contains the subjects at risk table. So a layout lattice was used to define a layout which had two cells. The first layout overlay created a layout for the KM curves, and you can use the step statement to create the 3 KM curves. If you look closely at the KM curves, you can see markers that have a plus symbol. These markers represent subjects with censored time points. In respect to overall survival, a censored value means a subject that is on treatment and hasn't died by the time the study finished. You can use the scatter statement to display the censored time points. You can use the discrete legend statement to produce the censored legend. Now, the second layer overlay is the container for displaying the subjects at risk table, and you can use the axis table statement to produce the subjects at risk table. Let's quickly go over some of the SAS code that we can use to produce the curve. As mentioned, we use the step plot statement to produce the KM curves, and within the step plot statement, the group equals stratum option is used to produce the KM curves for each treatment. Therefore, in the stratum column, there are 3 values because we have how many treatments? 3. Now, who can remember the color of the placebo group? Was it blue, red, or green? Put your hand up if it's blue. If your hand is still up, you're correct. The scatter plot statement produces the plus-shaped markers which represent the subjects with censored time points. You can see that the symbol equals plus option is used within the marker attributes option to create the plus-shaped symbols. Again, the group option is used to display censored time point values for each of the 3 treatments. How do we produce the legend which denotes the censored values? Some of you may be wondering. Yes? You can use the setup statement in conjunction with the discrete legend statement to produce the censored legend. Here, the markers option denotes the attributes which are shown in the legend. You can see that the option symbol equals plus and color equals black are specified, and so these attributes will appear in the legend. On the KM curve that I showed, there were 3 colors, blue, red, and green. However, instead of having a blue, red, and green plus marker, we only want to have 1 marker in the legend. That is why we chose a different color, i.e. color equals black, to represent the subjects with censored values across all 3 treatment groups. The name option is used within scatterplot statement to reference the plot statement in subsequent template statements, and it's used in our example so that the particular scatterplot statement can be eventually referenced in the discrete legend statement. Hence, the attributes of the markers displayed in the legend will be the attributes that we specified earlier in the scatterplot statement. To produce the subjects at risk table, at the bottom of the graph, you can use the axis table statement. In the axis table statement, you can use the class option so that the subjects at risk are shown on separate rows for each treatment group. The color group equals stratum option displays different color text for each of the groups in the stratum variable. Because the stratum variable is used here, and the stratum variable was used in the group options within the step plot and scatter plot statements, the subjects at risk text will be the same color for each treatment as the color of the KM curves and the color of the censored values, i.e. For the placebo patients, the at-risk values will be blue because the curve for the placebo patients are blue. So because I've produced the at-risk table inside the graph, but we produced it outside the main graph. That is the reason why we have used the layout overlay statement here as well. Because remember, this graph is actually two cells. The first cell is the chem curve. The second cell is the patients at risk table. Essentially, to produce this graph, we've used a layout lattice with two rows. So that is a layout lattice with two layout overlay statements. As mentioned earlier, the first layout overlay contained the series plot, scatter plot, and discrete legend statements, and the second layout overlay contained the axis table statement. Now we're on step 2. How do you create the log-rank p-values, hazard ratio, summary statistics table? That is a mouthful, and I'm going to show you. So you can create this table using the mvar statement and entry statements. The mvar, and that's the entry. Recall, we created 3 macro variables beforehand, and those macro variables contained the macro variable values of the log-rank p-value, the hazard ratio of the high dose versus the placebo, and the hazard ratio of the low dose versus the placebo. The mvar statements generate character tokens from the macro variables. Then the character tokens can be further referenced in GTL. For example, in the entry statement as shown here. So we're referencing the log-rank p-value character token. So therefore, the log-rank p-value will be shown in the plot. In the entry statement, you can also use the text attributes option to specify the attributes of the text, and therefore we have different attributes for different texts as seen in the P within the P value. You can see that the text attributes option style equals italic is used to make the P within the P value be displayed in italic font. The final step, how do we produce the lines which represent the median survival times, and also display labels which represent the median survival time? We can do this by using the nmvar, also mvar statement, and the dropline statement. The NMR statement is similar to the mvar statement, but it creates numerical tokens instead of character tokens. You may wonder why a numerical token was created. So numerical tokens were created because the dropline statement, which was subsequently used, expects a numerical value instead of a character value within the X argument and also within the Y argument. The dropline statement produces the horizontal and vertical lines representing the median and the median survival time. How does that work? A coordinate is used in the dropline statement, i.e. y equals 0.5 and x equals the median survival time, for example 69.1. Then, when the drop2 equals both option is specified, from that coordinate, it goes directly to the y-axis and down to the x-axis, and that's how that line is produced on the x and the y-axis. The line attributes options can also be used to format line attributes, and you also use macros within GTL, and therefore, instead of me writing the dropline statement 3 different times because there are 3 different median survival times and 3 different treatments, I can just use it, I can just write it once and wrap it within a macro. So the conclusion, data from a procedure can be saved in OGIS output objects to be used later on. As we've seen in this example, creating a custom template, and associating with necessary data allows you to create custom graphs quite easily. And it's relatively simple to create Kaplan-Meier plots using SAS. We use a step plot to create the actual Kaplan-Meier curves. We use a scatter plot to create the subjects which were censored, and then we used the discrete legend to display the legend. We use the axis table to create the subjects at risk. So it's very simple. And I just want to thank you for attending this presentation and watching this presentation online. If you have any questions, please contact me on LinkedIn or on this email address, ataljet125@yahoo.com.